Next important factor is temperature and rate of reaction. We know that in summers our milk gets sour very easily. As compared to winters, we can keep whole day our milk outside, no problem. But in summers, in a few hours, milk will go bad. Why it is so? With increase in temperature, rate of reaction increases because enhanced reaction rate constant. It means the reaction rate constant increases with temperature. And Arrhenius, a scientist you see here, has provided justification and interpretation for it. That was his expression. Here, you know, this is reaction rate constant, which is equal to A exponential minus activation energy divided by gas constant into temperature of reaction. A is the Arrhenius factor or frequency factor that describes the number of times two molecules collide in a solution. And activation energy, EA, is the energy barrier that reactant has to cross for conversion into products. Here we have taken an example of hydrogen and iodine reaction. These two molecules react with each other, and this is the potential energy one side, and the other side is the reaction of coordinates, or the reaction from one stage to another stage, time, or we can say. Here reaction goes to activated complex, which is a difference of activation energy between reactants and activated complex stage. And finally, from here it goes into products. We get hydrogen iodide as a completion of reaction from reactant to products. Delta H is the enthalpy change from reactant to products. Since reaction constant are temperature dependent, measure reaction rate constants at two different temperatures. We measure these Arrhenius reaction rate constants at two different temperatures. K1, which is at T1, Arrhenius factor remains constant. At temperature T2, now we subtract these two equations. Log K1 minus log K2 minus exponential activation energy RT1 minus EA by RT2, 1 by T2 minus 1 by T1. That's what we get, T2 minus 1 by T1. This is activation energy by R log K1 by K2. This is expression for calculating reaction rate constant at a particular temperature. Let's say we know K2 at temperature T2. Now we want to calculate at T1 temperature. We can calculate it because activation energy will remain the same. Only that reaction constant will vary according to temperature. Two scientists known as Max Kruse and William Lewis, they tried to explain the chemical reaction on the basis of collision theory, that is kinetic theory of gases. We know for reaction to happen, molecules have to collide with each other. Now, collision frequency is the number of collisions per second per unit volume of a reaction mixture. That's the collision frequency represented by ZAB. If collisions will cause the rate of reaction, because number of collisions between all the molecules in a reaction are so high, reaction will be over less than millisecond, less than microsecond level, the reaction will be complete. So because so many collisions are happening simultaneously, so it means all the collisions are not effective for creating a reaction or for making a reaction to happen. Out of the total collisions, only molecules with energy sufficient to cross activation energy barrier will convert into products. Let's try to understand it again with the graph. On our ordinate or y-axis, we have a fraction of molecules that is having energy, different energy levels, and this is a x-axis is active kinetic energy of our molecules. This is fraction of those molecules. As we go from here, you see this is a plot known as the Boltzmann-Maxwell plot for the behavior of large number of molecules at a particular temperature. This is called the most probable energy. Maximum molecules having this energy level, and as the energy of molecules increases, their fraction will keep on coming down. So this is the highest energy molecules. I have mixed it lowest fraction. Next is, again let's try to understand it. This is at temperature T, and only molecules with energy higher than activation energy. So only these many molecules having energy greater than activation energy. So only these many molecules can be converted into products. That's the activation energy barrier. If we increase the temperature, we see one tremendous change. The most probable energy shifted to higher energy level. The fraction of molecules with kinetic energy is here, and most probable the most of molecules having kinetic energy shifts to here, and it flattens also, mean the fraction of molecules having the most probable energy has come down, but the molecules having activation energy greater than this activation energy level, number of molecules with the activation energy greater than this level is higher. So it's almost doubled, you see here. The number of molecules has almost doubled with rise in temperature. Just 10 degrees Celsius rise in temperature. That is the reason. Now at a higher energy, these molecules can be converted into products. So actually, with just rise in a small temperature, the fraction of molecules possessing energy greater than activation energy level are almost doubled. That causes massive change in reaction. When temperature is raised, most probable energy molecules moves to higher energy value, and proportion of molecules with energies greater than activation energy increased. But still, the collision theory needs to mature. Rate of reaction is given as the fraction of molecules undergoes collision having energy greater than activation energy. That's what we understood from Boltzmann-Maxwell graph. But this concept is true only for atomic species or simple molecules. Significant deviation is observed for complex molecular reactions. Like in complex molecular reactions, there is another factor. Threshold energy is nothing but activation energy and proper orientation. If a molecule do having the right energy higher than threshold energy, but still, if it do not have a proper orientation, it will not be converted into product. that we see here. It's one molecule, and this is another molecule that makes a reaction. If it interacts this way, reaction will happen. This orientation, when it happens, in same plane headwise, no reaction, or it reacts from different angle, no reaction, or the molecule inverses, the small particle comes back, heavier particle goes up, or halide side, there is still no reaction. So right orientation is equally important. Out of all these probabilities, you see, only one particular orientation will only give us product, because here this small molecule can interact with the pi bonds. So this how the reaction will proceed. Protonation is only possible if the pi bonds are oriented toward proton. So the reaction rate will be equal to P ZAB, which is the frequency factor, into exponent into activation energy divided by gas constant into temperature T, where T is measured in Kelvin scale. P is a steric factor or orientation factor. ZAB will be collision frequency. Now, catalytic activity, effect of catalyst on chemical reactions. We know a catalyst is a substance that alters the rate of a reaction without itself undergoing any chemical change. Same, this is energy on y-axis and reaction coordinates, which is nothing but the reaction at different times. Here we see a reaction goes from reactants to products. This is an activation energy level without any catalyst. Reaction proceeds in the presence of catalyst. You see, activation energy has come down. So it means what happens, we just saw in Boltzmann graph, the molecules that having a lower energy will go down sufficiently high. We know the number of molecules possessing a lower energy were significantly high. Definitely rate of reaction will be faster in that case. That is the reason when activation energy comes down, rate of reaction will go up tremendously because of increase in frequency factor and reduction in activation energy that increases the number of molecules with higher energies. Important point to remember, what catalysts do. Catalyst does not alter the Gibbs energy, which is a delta G of a reaction, which means if a reaction is not feasible thermodynamically when delta G is positive, then that reaction will not proceed with catalyst. Catalyst does not make a non-spontaneous reaction spontaneous. It's not possible. It doesn't alter the Gibbs free energy. What catalysts do is, it provides an alternative energy path for a chemical reaction. That's what we just discussed. It doesn't make a non-spontaneous reaction spontaneous. It's not possible. It simply provides the alternative lower energy path for reaction to proceed and help the reaction to achieve equilibrium quickly. It doesn't change the equilibrium point even, just it helps to attain equilibrium quickly. That's what all our catalysts do for a chemical reaction. It increases the forward and backward reactions with the same, so the equilibrium position will remain same. Only it helps to attain reaction equilibrium quickly. We just think like that. If we having a catalyst or making iron rust, whatever naturally rust happens make it to happen just in minutes or days rather than in years. And in case of manufacturing of ammonia, if we naturally want to obtain ammonia, definitely it will happen, but it will take a fairly long time and different conditions are required for it. But when we add a catalyst, equilibrium constant will not change. Equilibrium constant is fairly small, but with catalyst, reaction makes up faster, and we utilize the Lee-Chatelier principle by constantly moving the ammonia, so that equilibrium will always keep on shifting toward ammonia. So use of catalyst and Lee-Chatelier principle helps to manufacture ammonia cheaply